There we go. Okay, so what we're finding is the angles between lines in three-dimensional space, right? And if you're thinking about lines in three-dimensional space, they might, they could be parallel, they could be coincident, they could be perpendicular, but most likely, they're probably not even touching at all. All right, so you look at these two lines, they're going infinitely in both directions, they're never going to touch. How do you find the angle between them? All right, so what we're doing is we're using a technique we learned in year 11 called projecting. So let's say we've got this line here that is sitting on this plane, and we have this other line here that is not touching it, it's not existing on the same plane. What we're doing is we're projecting this line onto this plane so that they share the same plane, and then finding the acute angle between them. So that's what it means when we're finding the angle between lines in three-dimensional space. So we've got a formula to crank out. Okay, question 1, find the angle between the line. Here's our first line, 302, and its direction. The direction is 1, 0, minus 1. Now this, just to clarify, this is the vector form of a line because we're given a direction vector and a coordinate. So this is vector form of line 1. And line 2 is given to us in parametric form. We're told x equals 2s, where s is some parameter, y equals 1 take s, and the z value is just equal to 3, always. Okay, so B1 and B2 in our formula up here, they're not bananas, these are direction vectors. So this is the direction vector of line 1. The direction vector of line 2 is going to be the coefficients of s. So we have 2, minus 1, and 0. So these are B1 and B2, and all we're going to do is crunch them into our formula above. First we have the dot product of B1 and B2. I'm just going to write the whole thing out here. So the dot product is going to be 1 times 2 plus 0 times minus 1, and then plus minus 1 times 0. And the modulus of that, that's what's going at the top. And then at the bottom we have the modulus of each vector. So this one will be root 2, and this one will be root 5. 2 squared plus 1 squared. Just simplify that a little bit. We have cos theta is, we have the modulus of 2 at the top, so we'll have positive 2 on root 10, and we'll evaluate the theta. In degrees or radians, doesn't matter, but we just need to make sure we specify which one we're talking about. So let's evaluate that. I've got 0.886, so that's radians. And of course we use C for radians intuitively. Alright, so that's our answer to question 1. Alright, for question 2, we have two-dimensional lines. So we have find the angle between the x-axis and the line y equals 2x. Okay, so Cartesian plane, here's x, here's y equals 2x. So what that means is it's going across 1, up 2, across 1, up 2. So this coordinate here is x is 1, y is 2, 0, 0, y, this is the line, y equals 2x. And we're asked to find this angle here. Now I'm going to show you two techniques. We will use the vector techniques that we've been talking about. So if you consider the line y equals 2x, all right, what that means is it has a slope of 2 on 1, and what is slope but change in y divided by change in x. And so the direction vector then, that results from a slope of 2 on 1 is across 1, up 2. Okay, so that's the direction vector of the line y equals 2x. And the direction vector of the x-axis, it's just going across 1, up 0. We can put any constant here, all right? The x-axis is just going across, and it's not going up or down. So we have two direction vectors, and we're just going to repeat this formula here. So we need dot product of both of them. So we'll have cos theta is 1 times 1 plus 2 times 0. All right. Modulus, and that's on top of root 5 and root 1. And so we'll have 1 on top of root 5. Evaluate the theta. Got 1.107, 1.12 radians. Okay, let's talk about the other procedure with which we can think about this. All right, we want the angle between these lines. So let's abstract that triangle, and you can see we've gone across 1 up 2. We want theta, so we'd go, if we label the triangle H, A, and O, the trig ratio involving O and A is tan, so we would have tan theta is O on A, inverse tan. Get us the same answer, but I just wanted to bring up the technique that we've learned today. Okay, last one. We have find the acute angle between the line 1 here, and all I'm going to do straight away with line 1 is I'm just going to take the direction of it. All right, so the direction of line 1 is t, so that's what I've got 1 log of t for the x value, 1 log of t for the y value, and 4 logs of t for the z value. So that's the direction of line 1. Now for line 2 is written for us in Cartesian form, and so let's discuss how we can move from this again back to, so we have x take 3 on minus 1 equals y plus 1 on 2 equals z take 1 on 2. Okay, so the way we move from here to parametric or vector form is where all we're doing, because they're all equal to the same parameter. So we'll have x take 3 on minus 1 is equal to s. All right, y plus 1 on top of 2 is equal to s, and z take 1 on top of 2 is equal to s. And basically, when we go through to solve this, we'll have x take 3 equals minus s, and then we've moved that 3 over, we have x is equal to 3 plus s, but the direction component, all right, of this is, that's still negative. 3 becomes positive. The direction component is minus 1. Over here it's going to be 2. We have y plus 1 equals 2s. Y equals minus 1 plus 2s. Okay, so the direction component of this one, positive 2, and this one is going to be the same. Okay, so we've written it there in parametric form. We've got the x, y, and z value. But hopefully you can see the length. The direction vector is just this coefficient here. Okay? Minus 1, minus 1. 2, 2, 2, 2. So they're all connected, the forms of presenting the line. Alright, so then we've got two direction vectors. So this is our first one, and our second one is minus 1, 2, 2. Let's do the calculation. So we'll have cos theta equals now the dot product and then the modulus of it. Modulus of the first vector, so what's that, 1, 1, and 16 is root 18. And the second vector, 1, 4, and 4 is 9. So what have we got here? Minus 1 plus 2 plus 8. So that's 10, 9. So we have 9 on top of 3 root 18. And we find the inverse cos. got pi on 4. Pi on 4, 45 degrees. Very good. Okay, let's rip in. So that's 6C. I'll float around, see how everybody's feeling about what we've been going through. And hopefully we can have a look at 6D today as well.